Welcome to this set theory primer. We will continue our discussion from last time. And well, we didn't do much the last time, so there is not much to recall. But anyway, so we looked at the notion of a set and we looked at the notion of belongingness. So given a set and some well-defined mathematical object, you can always ask if that mathematical object is in the set X. And yeah, so this is just a notation which means that A is in X, or alternately A is a member of X, or A belongs to X, or what else can you say synonymously? A lies in X, maybe you can say, etc. So all of these things are the same things, and more or less this is what we did the last time. Here are some problems for practice. So yeah, we also looked at the notion of roster form and set builder form, and these exercises will help you, get some practice as to when to go from or how to go from one form to another. So these are written in builder form. Can you write down the roster form for it? And this will help you exercise your brain so that the builder form is something that you get comfortable with. All right. So we will look at more notations and key definitions that are generally used all the time. One such thing is quantifiers. So this symbol is a shorthand for all or for every. So when we write this inverted A, we just either mean this or that or something similar, like for each. You can also say for each. Depending on the context, whichever fits the best, that is what it abbreviates. So an example is, for all x in n is the set of natural numbers. Recall this is this set, all natural numbers. So for all x in n, which is another way to say that for all natural numbers x, we have this inequality, which is trivially true because every natural number is at least 1. So I'm just illustrating the use of this symbol. Instead of writing for all, we just make the symbol because it is more economical. That's all. And this is called the universal quantifier. Just a fancy name. All right. This stands for there exists. Shorthand for there exists. Or there exist, depending on which is grammatically correct. Or there is. So this statement reads, there exists x in this set such that x is at most 4. So this is a true statement because 3 is in the sky, which is less than 4. So yeah, this is just a shorthand again. This is called the existential quantifier. There is no space, but I'll manage. Existential quantifier, just a fancy name again. Okay. This is not a quantifier. This is shorthand for implies or a synonym of it. So let's see an example. X is a crow. Crow, the bird crow, implies that X is black because we are assuming that all crows are black. Of course, you can always find a crow somewhere which is not black because it's an albino crow or something, but try to understand what I'm trying to say rather than find faults at every little thing. A more unobjectionable statement would be x is greater than equal to 4 implies that x is greater than equal to minus 2, clearly. So it's just, a nice shorthand for this thing. And, sometimes someone may replace this by some synonym of implies, and that's okay. This is if and only if. So one also reads it as double implies, and it is nothing but, so I'll explain a little bit more, but let's see an example. So x square is equal to 9 if and only if x is either plus 3 or minus 3, right? So if and only if means first you write if here. So x square equals 9 if this is true, clearly. And x square equals 9 only if x equals plus minus 3. So both statements are correct, and this just writes both of them in one shot. In other words, whenever you have something of this format, that some mathematical statement A, this symbol, and some mathematical statement B, this is exactly the same as saying A implies B and B implies A. So these two statements together is that statement. So A itself is a mathematical statement, B is a mathematical statement, and this whole thing is also a mathematical statement. What I'm saying is that this is same as that. Okay. Subsets. So it's a very natural concept. Suppose I have a set B, then we say that A is a subset of, so this is read as is a subset of, just a shorthand for that, if for all A in A, we have A in B, meaning every element of A is an element of B. Right? That's what a subset is. If everything that is there in A is also there in B. B can potentially have more things, but it also has, it certainly has everything that is there in A. Another way to write this is that, so A in A implies A in B. It's the same statement as that one. And let me plant a flag here that when we write this includes the possibility that A equals B. So that's completely fine. And in many textbooks, when we write this, in many textbooks, this is just written as that. So there is no difference between this and this. Okay? But I always put this guy here. All right. So let's see an example. This is a subset of natural numbers because everything here is a natural number. So that's clearly true. And here is a very simple lemma. If A is a subset of B and B is a subset of C, then A is a subset of C. In words, it just says that if everything in A is in B and everything in B is in C, then everything in A is in C. And that's intuitively clear. But if one insists on a formal proof, one could say let A in A be arbitrary. Want to show that, this is an abbreviation for want to show that A is in C. So if we do this, then we will have shown that A is a subset of C, because then every element in A would then be an element of C. But since A is a subset of B, we have A is in B, because this is in capital A, so it has to be in capital B because of that. And then again, since B is a subset of C, we have A is in C. And that's it. So that's a formal proof which was not needed, but I still do it because this is probably one of the first lectures in higher math that you are seeing on this channel anyway. Okay. And let me also introduce the notion of proper subset. So we say A is a proper subset of B if A is a subset of B and A is not equal to B. So there is something in B which is not in A, but everything in A is in B. That's what it means to say that A is a proper subset of B. And when A is a proper subset of B, we write this and then slash it out and write B. So this just emphasizes that A is not equal to B, but still it is contained. So maybe I should just slash out the lower guy that way. So that's so that's the notation for proper subset. And now we come to the notion of a power set. So let A be any set. The power set of A is defined as the collection or the set of all the subsets of A. So A is a set, hence it has subsets. Collect all possible subsets of it, including the empty set. That is the power set. So let's see an example. We are trying to find the power set of the first three natural numbers. So first of all, it has the empty set. Let me denote that by phi. Then it has this set, that, and lastly. So the power set is a set which contains sets in itself. And as we had said earlier, that a set may contain other sets, that is completely fine. And this is one such example. So yeah, I think this is enough for this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.